Alright, welcome back to another video. There's gonna be two videos that you're gonna watch today, and today's is pretty interesting because today we're gonna be talking about compound interest. And compound interest is from a concept where um you take consideration of time to let things grow. So some things are very popular within the realm of compound interest is like student loans or any kind of loan in general, or like any kind of investment. So it's applicable for our class today to talk about these things because we have an equation that people use in real life and to calculate a lot of things, like such for example my investments, which maybe I'll show you guys later. So today you're going to be learning how you'll be able to formulate exponential equations that model real world situations. So the real world situations is talking about investments or student loans or blah 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 blah. So last class we talked about attributes of a exponential equation. So today we're going to be applying um, real world situations within exponentials. So first of all, we're gonna be talking about just compound in general. So let's say, for example, you compound once a year. So the equation would be a times 1 plus r to the power of t. And I'm gonna be labeling these things, or I guess I could put p. I'll put p. P is a little bit better because it aligns with my paper. So A is the amount after time. So the key phrases is the amount after. P is the principal or the amount before. That's the P right here. The rate of growth is R, so I'm going to just write rate of growth. And one thing you have to have is this needs to be in decimal. And T is time periods. I'm going to give you this other equation just nicely and neatly. So this is A times, or sorry, P times 1 plus R over N to the power of NT. And the only difference between, well, this equation here, the compound once per time and the compound n times per time, is the n. So this n is talking about how frequently per year. So so think of it as like, if we're talking about if we're talking about years and we say that compounds monthly, we can say that, well, there's 12 months is equal to 1 year. So therefore, n is equal to 12. So yearly, most likely n is going to always be yearly. So n is equal to 1 because there's 1 year in a year. There's 12 months in a year. There's 4 quarters in a year, which is split off by seasons, such as like winter, summer, fall, spring. Not in order, but you know what I mean. Weekly, there's 52 weeks in a year, and daily, of course, there's 365 days in a year. So lots of general, very basic information, and just so that I don't make the video too long because it's already been 5 minutes, let's try these examples. So example 1, Brandon buys a house for $96K, in 1995. Real estate. He'll grow his house in 4% per year. What's his year in 2007? So not too bad. Just a very basic generic question. So one thing we do need to know is that you have approximately gaining 4% per year. So if we're talking about years to years, so this is the time unit that we talk about, and this is the how many times how it grows. So it increases approximately 4% each year. So we know that n is equal to 1. So now we can use this formula is equal to p 1 plus r over n times nt times the power of nt. Well, if n is equal to 1, and they're asking us what was his value of a house be after this time right here, because he put in $96,000 before at 1995. So 1 plus, well, he says it's 4%. So 4% is the same as 0.04. So 0.0, here you go. 0.04 divided by 1 to the power of 1n, which is 1. And, well, I need to figure out what's the difference between 1995 and 2007. So 2007 subtracted by 1995. I have anxiety, so I'm going to use my calculator. 2007 subtracted by 1995, that's 12 years. That's 12. Like that. So very easy. All I gotta do now is plug it into the calculator. So I'm gonna bring this to the side like this. Calculator. 96000 times 1 plus 0.04. I'm gonna put this in parentheses. To the power of 12. So the house is about so what is this? 15 153 153 699 0.09. So this is how much money his house would be now. So from $96,000 to, you know, almost 16 or 160,000, 160,000, yeah. That's a lot of money. That's almost $70,000. That's almost half of the money that he put in. It grew in 12 years. So that's pretty good. So we calculated that using math, and this is a real equation that people use, that I use personally. So, you know, it's pretty cool to see that he grew with only 4% yearly growth. I would like for you to try number 2, but number 2 is talking about decreasing. So I guess what I would like for you to do is to label all of your variables. So AT, principal, rate, time, N. These are the variables I would like for you to try to label. So let me give you some time in 5, 4, 3, 2, 1, and you can resume the video now. Okay, so number 2, I labeled my variables because, well, they're talking about the year 2020 having this many people. So that's my investment or my initial amount before. And they're asking me how many people are going to be alive in 2050. So that's how I know that this is going to be my answer, or like the answer to the question that was presented in my well, in example 2. Well, I know that R is going to be negative 0.005 because 0.5% is the same as, well, if I change it into decimal place, 0.005. But it's also saying decreasing. So I made my rate of change negative. The time here between 2020 and 2050 is 30 years. And this happens every year. So every year means 1 for n. So now I'm going to replace everything with the equation. 1 plus r over n to the power of nt. So I'm going to put, yeah, x is equal to 705,400 times 1 plus, not plus, minus, and that's because of the 0.005. That's negative. My rate is negative. This is a 1 right here. To the power of 1 times 30. Good. So let's try to put this into Desmos right here. Instead of me like rewriting everything, I'm just gonna replace the numbers like this. I replace this negative with or positive with a negative. This is gonna be 0.005, and this is gonna be 1 times 30. So this ends up being ends up being 606,915. Yeah, people. Residents. Oh my gosh. Residents. So if the pattern stayed the same, so every single time we lost 0.5% of people each year for the population of the city of Denver, um, from 700,000 people, they would lose 100,000 people to here. So it makes a lot of sense. So say that you put, this amount of money. Yeah, I put about $1,750 into a savings account, and you earn this much percent value, which is pretty true, but it now compounds monthly. So how much money would you make in a year, in 5 years? So when I try to label my variables, so of course, how much money will I make after 5 years? This is going to be my question mark right here, which is pink. My time is 5 years because it said so in the question. How long after? 1750 is gonna be my initial investment, and the rate is gonna be positive 0.008, and that is because of my rate here. So because this is compounded monthly, my n is not 1. Because now I have to question myself, well, what's the relationship between years and months? So 1 year is the same as how many months? Question mark. Months. And this is going to be my n, which is right here. Well, that's 12 months. So that's why my n is going to be 12. So the reason why we've been doing this equation for the past two questions um, is because whenever I have my n here, so if I have a to the power of at is equal to p times 1 plus r over n and t, you won't be having too much trouble labeling everything. So this is right here. The rate is right here. The time is outside. And the n is here, two places. And of course, the answer is the pink. So it's going to be x is equal to 1750 times 1 plus 0.008 divided by 12 to the power of 12 times 5, which is really 60. So I'll leave that there for now because, I mean, the calculator is going to do it for us. The whole idea behind this lesson is, can you put the variables where they belong? So now, 1751 plus 0.008, and of course this is a 12 now outside, 12 times 5. So if you make like 0.8% monthly for 5 years from $17,50, you will come out with $18,21,39. So just you doing nothing for 5 years, you do nothing, and your money is just sitting there. You gained almost $100. That's not too bad. You did nothing to do that. You just kept your money in there. So number 4, I would like for you to try yourself. So the numbers are still the same. So 1700, the rate's the same, the years are the same, but this time we're compounding weekly. So instead of monthly, so all your variables are the same. The only thing that's different is your n to be different. So I would like for you to try that yourself and compare it to number 3. So who made more? Number 3 or number 4? So let me give you some time to try that. So you can pause the video at this time, and I'm going to reveal the answer in 5, 4, 3, 2, 1. Okay, so we're back, and I see the example 4 made 2 pennies more than example 3. So yeah, I would choose example 4, and the reason why that is because being compounded more often results to more equations being applied to your total amount of money. So that sounds really confusing, but I have this table for you here. So if we compare how often interest is compounded, so all these things right here have the same rate of, showing 100% interest on $1,000. You can see like, okay, if I do it annually, my money just doubles. Or if I compound it annually. But if you compound it monthly or daily or minutes, even to seconds, you can see that I made the same amount of money, or I made more money in the same amount of time. My time is just 1 year. The only thing that's different is that, well, n is equal to 1 here, n is equal to 12, n is equal to 365, and n is whatever. It's growing. So the bigger your n, the more you're going to grow. And that has to make sense too because, well, we're taking into consideration of doing the equation and adding it upon each other, n amount of times. So only doing it once is only going to double your money, once. But if we take that equation 12 times per year, you're going to gain so much more. Like, an extra $600 is pretty good for you doing nothing. So there's an equation that we use to represent that. So what if we constantly did that over and over again? So instead of like every 30 seconds, we did it with every single instant in your life. You find this equation in the real world, like a bank account, you take it immediately. So this is called PERT, or the money after. There's equations that we have to, or variables that we have to label. And we labeled most of these. So this is the after, this is the before, this is the rate, and the time. But what is E? E is actually 2.7, and this is still going to be E, which is going to be now labeled like this, like a cursive E. Because on Desmos, you can see that, well, if I type E, it spits out 2.7 blah 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 blah, which is an irrational number, which we learned last class. So example 4 says, suppose that you won a contest in the 5th grade and you deposit $3,000 into your account for a 5% annual compounded consistently. The compounded consistently part, that's how you know that we're gonna be using PERT. So to the nearest dollar, how much money would be after 8 years? So I have to label all these things. So the rate is going to be 0.05. Investment is going to be $3,000 and 8 years. So it's going to be 3,000 times, I'll put the parentheses here, times e to the power of 0.05 times 8. And let's try it out. Let's see, 3,000 times e to the power of 0.05 times 8. So in 8 years, you made 4,000, or you made a total, well, you have now $4,475.47. Oh, the directions told me to round to the nearest dollar. So there you go. So you made about $1,475 in 8 years. Nice. So example 5. So Barbara Jean is investing $5,000 in her lottery winnings, and she's putting it into a savings account. Her interest rate is almost 10%, 9.75, and compounded continuously. So how much money would she have in 10 years if she didn't make a withdrawal? I would like for you to try this as our conclusion of the class. And I'll show you the answer in 5, 4, 3, 2, 1. And here you go. Um, Other than that, pretty good. Pretty good. Pretty easy. What I would like for you to do is do this transformation exercise that the sub has left for you. So you would be doing the attributes part that we learned before, and then now we're going to be doing, the only thing that's new is this transformation. And if you remember, last class, or a few classes ago, we talked about this table that's in my room. Like this. Where you have, like, for example, x squared plus 1, x squared minus 2, x minus 3, x plus 3 squared, x minus 4 squared. Then we have, like, you know, like 2 times x squared and 1/2 x squared. And last one, x that's negative. So what happens here is that, well, we talk about transformations. This will be like up one, this will be down two. The same thing applies here. And I would like for you to think of this as like, well, this right here is that point 0.5 is the same as this outside multiplying. So for example, this is going to be a vertical compression by point 0.5. And, well, there's no other transformations. So don't be baited by this 3. This 3 is not a transformation. This 3 is called the base. So that's why this is B for base. Let's try this number two. I'll show you this number 4. So number 4 has an, so this plus 1, this is adding, and this is outside. So if I look at the table in the look at this table, I need to look for adding and outside, which is this right here, and it resulted in my equation or my function going up 1. So the only transformation that happened here is up 1. Do not get baited by this 9 because the 9 is a base. So anything that is in the power or that is getting exponentialed, don't think of it as a transformation. It is just part of the base equation. So we're comparing 9 to the power of x to 9 to the power of x plus 1. That's all we're comparing to. So there's only one transformation for number 4. So I would like for you to try this, and I'll see you guys next time in another video or maybe at school. And I'll see you guys next time. Take care.